Okay, so yeah, I'm an associate professor at the University of Warwick, which is located just outside of Birmingham. And so I wanted to take today to talk to you about the various work that my group is doing. But I figured take a little bit of time to set the scene here, just in case there's any people who have logged on to the RCN for the first time here. Hopefully everyone's kind of familiar with the concept of exoplanets and the fact that we are pushing towards those lower mass, longer period ones, but we still have not found that elusive Earth 2.0. And we'll talk a little bit about the stumbling blocks along the way. So if you're interested in extreme precision radial velocities, you're probably familiar with this, but just the fact that the star and planet share a common center of mass, so the planet causes the star to wobble about that center of mass. We observe the starlight, and then we are looking at where the starlight is being absorbed in the stellar atmosphere and measuring the position of that over time, and essentially looking at the Doppler shift of that. And where the starlight is being absorbed, we get this stellar spectra, something like this, thanks to Sam for his example. So we could measure the centroid of individual lines and then combine that information to be able to beat out sort of uncertainties that we have on individual lines, or we can do a cross correlation with some sort of template to build us up with some like a super precision, and we get something called a cross correlation function, which we can think of as like a composite line profile that contains information from all of the lines and is far more precise. But you can imagine if there are any asymmetries in the individual stellar lines, those will propagate through into the cross correlation function. And whether you're measuring individual line velocities or the cross correlation function, those asymmetries then can show up as spurious velocity shifts if we don't account for them. So what is the sort of magnitude of scale we're looking at? Just popping up 51 Pegasi b as a quintessential hot Jupiter being the first one that we know about. And looking at this y-axis scale there of about plus or minus 50 meters per second for that signal. And then if you zoom in, this is where we're looking for if we're trying to find an Earth twin. This is the elusive 9 centimeters per second signal. And now I want to show you an example of what this would look like if we took the sun and we said, okay, let's observe the sun as if it were a distant star. It's a great example because we have the highest precision data there because we have the best signal to noise, but also it's the only system where we know all of the planets, plus or minus 1. And then we can make sure that when we subtract off those planetary signals, any velocity that we're measuring left over is coming from the star itself or a contribution from the instrument uncertainty. And this is what that would look like if we were using the Harps-Norris spectrograph to observe the sun as a star. And of course, all that variability that you're seeing there is because our sun is not homogeneous. I mean, you can see the size of the error bars there compared to the variability. Like we're dominated by stellar surface changes. And really, you can see that has been a prolific problem throughout since basically like the last 10, 15 years. So this is a nice plot from Analysing material. We're showing the semi-amplitude of the planetary signal versus year of discovery. And of course, if you're sat in this audience, you probably know that we've kind of stagnated at this 1 meter per second barrier. And if you're interested in pushing towards that 10 centimeter per second precision, we really need to start understanding the star a bit more there. So where does this come from? It's all driven essentially by convection and its interplay with magnetic field. So this is a nice set of observations from the Ditka Solar Telescope showing you disk center of the sun, and the X and Y scale there is about 30 megameters. And an individual granule is about a megameter, 1,000 kilometers across. And you have these hot bubbles of gas rise to the surface, cool and fall back down. And when they're rising towards the surface, they're blue shifted as they're coming towards us, and then they're red shifted as they fall back down. Overall, there's a net blue shift because the granules are brighter and cover more surface area, as you can see in the image here. So that convection, it does a few different things. Not only does it have that net blue shift, the convective motions themselves cause broadening in our stellar lines. This has been referred to as like macroturbulence in the past, but we can use actual 3D magnohydrodynamics to understand it as more than just a fudge factor here. It's not just a turbulence, but that's a first order, there's a broadening effect. And then you get this asymmetry as well because of the imbalance between the bright upwelling blue shifted granules and the dark downfalling intergranular lanes illustrated here, as well as there's something known as like a universal relation for convection, where you've got flux on the y-axis versus velocity, or like your net convective blue shift on the x-axis. And basically any star can be scaled to this plot, and the scaling factor tells you about the velocity gradient of the convection. So it's an interesting way that you can actually get absolute velocities of other stars, as well as learn about the convective properties on those stars and what their flow velocities are compared to the sun. In addition to just small scale granulation, we have this happening on a larger scale, known as supergranulation. You can see it here in this SOHO Dopplergram, where I kind of like to show this diagram from one of the reviews on supergranulation from the sun, where you can see you have these like networks of really large granules. So they're like collections of the individual granules, about with a diameter of about 30 megameters. And then you've got sort of magnetic field that is flowing, that's kind of concentrating around the perimeters of these supergranules. So you'll often see magnetic bright points on the perimeters of these supergranules. And you have upwards flow velocities about 30 meters per second, and then horizontally about 300 meters per second. And so at this center, there's not that much contribution, but towards the limb, you get quite a bit more. And like that small scale granulation or convection has lifetimes of around 5 to 10 minutes or so, whereas these supergranular cells live for closer to 2 days on the sun. But we don't really know for sure its origin, and we don't really understand how it propagates on different stars. And then the fact that we have convection excites these pressure mode oscillations. So you have the surface of our sun and sun-like stars ringing with a characteristic frequency. For the sun, this corresponds to about 5 minutes. And the granulation variability for our sun is on the order of around 50 centimeters per second or a little bit less, where the P-mode oscillations and radial velocity spikes are on the meter per second. So they're larger in amplitude, but they can also be averaged out more easily. And then what happens if you take a patch of your regular granulation and then you add a bit of magnetic field? Well, if you add enough, you can suppress the convection so much that you get a cool region, and that manifests then as a dark star spot. Alternatively, if you don't completely alter the heat flow that much, but you're just changing the opacity by having an increased magnetic field, then that can allow you to look deeper into the star where the star is actually hotter. And so at this center, this would manifest as magnetic bright points. And then at the limb, this shows up as faculae or plage, which are these sort of brighter regions, and that you often see them accompanying spots. Spots will essentially decay into faculae, but faculae may not necessarily turn into spots. You can see faculae on their own, but unless your star is really, really spotty, you're going to have faculae accompanying your spots. And for the sun, our sun is actually faculae dominated, as many here probably know. So what does this look like in terms of the spectral or maybe the cross-correlation function that you observe? Well, you've got your star that is rotating. So you've got a blue shifted hemisphere and a red shifted hemisphere that's going away from you. If, for example, like in this cartoon, you had a dark patch, then you have less light to be absorbed. So you end up with an emission bump, and that changes the asymmetry of your line. So if you were to go measure the centroid of this, you could get a spurious velocity shift. Now, in addition to this, you have the fact that your convective velocities are inhibited. So that net blue shift goes away, or at least is suppressed significantly. So it's a twofold effect going on there. And then, of course, all of this is modulated over over a magnetic activity cycle. This is just showing you some work from Nadesh Meunier and also some work from Raphael Haywood, looking at some solar physics data where you can see that over the course of a solar cycle, like this sort of big amplitude of almost 10 meters per second is over the course of a cycle. And then the variability you see on the shorter time scales has to do with the rotationally modulated variability. So the fact that you have starspots and faculae that are tied to the stellar rotation period, which for our sun is about 27 days. And again, this is the signal of our Earth that we would be trying to pick out on other sun-like stars. So it's kind of like trying to find a needle in a cosmic haystack here. So that was a sort of a brief 10-minute summary about like stellar variability in a nutshell. And I want to talk to you now about like the work that my group is doing in this area. So I've got a PhD student, Ginger Frame, who is working from the simulation side of things. And then Dr. Vedad Konovac is working on the Rossiter-McLaughlin side of things. So looking at spectroscopic transits. And then Dr. Vatsopanwa is looking at exoplanet atmosphere measurements. So again, looking at this from the observational side of things. And then coming soon, I will have another PhD student joining my group working on stellar variability, as well as an incoming postdoc that will be working hopefully on the MHD simulation side of things. So why are we focusing on granulation? Not only is it because it's sort of the foundation of every other bit of variability, but because it's also quite tricky to average out. I like to show this image. Some of you have probably seen it before, but in this bottom right hand, you've got a single G-band exposure of the sun. And then you've got different filters here, but 1 hour time averages. And you can see that even just visually, after averaging of over an entire hour, you still have a lot of structure there, which you can see how that would translate into still having correlated signal or noise left over in your data. And there's some work by Nadesh Meunier that says that, okay, you probably, if you wanted to get down to the 10 centimeter per second regime just from binning, you would need to average for 8 hours or more a night. So it's really not an effective way of dealing with things, which is why we come at it from a simulation point of view. The simulations are particularly useful because, as I mentioned earlier, the sort of amplitudes that we're looking at are of the several tens of centimeter per second. And with the best EPRV instruments today, we're struggling to get below 40 centimeter per second precision in terms of like an absolute sense, which means that it's really difficult to probe granulation on other stars. Because it's hard to separate between what is the instrument doing and what is the granulation. It's not impossible, and there are many exciting avenues to go down there and people doing that. But if we go from a simulation point of view, we're not limited by the instrument, and we're also not limited by resolution. So we can have resolution of like 1 million or something, and we can go to different spectral types. So although we would have the best resolution and the best signal to noise for some of solar data, we can do this on stellar data as well. So I'm just showing you an example here of some old simulations from MIRAM. They're 3D magnetohydrodynamics, so it's by 12 by 12 megameters. There's a plot of Europe to scale here, courtesy of Chris Watson. And then just showing you against the backdrop of some solar observations, so you can see how realistic these things really are. And the premise essentially is just to take the output from the 3D state-of-the-art simulations and populate them over some stellar grid, and then you can integrate over them, and then that will give you a model sun as a star observation. And then the idea is we will do stellar line synthesis on each of these individual patches of stellar atmosphere, and then we can look at the line asymmetries to diagnose like the best way to deal with the granulation RV contribution to our signal. And so I'm showing you here some old movies where we've got basically the 6302 iron line that we've populated throughout here, and we integrate up, and then you can see it should be bouncing around, but it's hard to see by eye. So I've overplotted the bisector, zoomed in by a factor of 30, I think. And so for a reminder, the bisector is you take horizontal slices and you grab the midpoint. So if you had a perfectly symmetric line, that would be straight, but the convection and the imbalance between the upwelling bright granules and the dark infalling intergranulating gives you this characteristic C shape. And then when you zoom in by a factor, I think 10,000 or something, you can see that the line really is bouncing around. And from our proof of concept work, we showed like, okay, actually, if you look at, like, for example, I'm just showing you some measure of the curvature of the line versus the velocity that we measure for that line, there's quite a strong linear correlation. And if we just remove that linear correlation in a not very intelligent way, we can reduce the variability from the granulation by 60%. And now, of course, that was just one line in one magnetic field. So the idea is to expand upon that work. And I'd also point you to, there's a series of papers by Dana Stravens that is taking a sort of a similar approach using hydrodynamical simulations. So I would definitely recommend you check those out. So Ginger is going to be looking at Miram cubes. So we can either do pure hydrodynamical, which you can see as an example in just a snapshot of a continuum here. And here I'm showing you we have 512 by 512 pixels resolved into what is actually 9 by 9 megameters. So we're a little bit higher resolution than the proof of concept work. And then we also have small scale dynamo cubes as well. And so these should be more realistic than the hydrodynamical because we have a bit of magnetic field in there. And it should be more akin to what we think the magnetically quiet photosphere of our sun is. And then we also have cubes where we've increased the magnetic field up to 100 Gauss and 200 Gauss. And you can see how it's starting to change the structure of the granulation here. So the impact of the magnetic field is it alters the flow velocities and the temperature structures. And then that ultimately is going to change the line shapes of the observed stellar spectra as well. So we've also switched a little bit into using a different line synthesis code when we can. So we're working with Veronica Ritsky and Gertinem and using her code MPS Atlas, which is an upgraded version of Atlas that can be much faster. So I'm just showing you an example here of the wavelength coverage that we could possibly be doing with MPS Atlas. So we were previously using a line synthesis code called Nicole. And so when we use Nicole, we're doing one line at a time. But with MPS Atlas, we could choose to do an entire shell spectrograph that maps to an EPRV instrument. And actually, although this goes up to 2,000 nanometers, we can actually go up to 10,000. So it can really do quite broad wavelength coverage here. And then just showing you on the side here, a comparison to some observations. So in this case, we were comparing Miram to observations. And then in this case, we're just comparing MPS Atlas with different line lists where we've assumed certain properties between the Karuts line lists and the Vald line lists. But really, another good way to look at like how well this code works is to compare it again to observations of solar lines on an individual side. And so I'm showing you the bisector of two different iron lines, and they're not particularly magnetically sensitive. I've got the Landé factors here, and you can see though that the FTS observations match really quite well the combination of Miram and MPS Atlas. And the Miram simulation that is underpinned here is a small scale dynamo, and the observations are the quiet sun. So you can see we've got a pretty good agreement there observationally. But the main difference besides speed between Nicole and MPS Atlas is that the Nicole code can take into account the Zeeman effect. So the fact that you've got that broadening because of the magnetic field there, whereas MPS Atlas does not. MPS Atlas will capture the fact that the temperature structure and the velocity structure have changed because the magnetic field has changed, but the specific aspect of the Zeeman effect is not captured in MPS Atlas. So what Ginger wants to do is ultimately she's going to be comparing hydrodynamical simulations to small scale dynamo simulations and trying to figure out like, okay, are hydrodynamical simulations good enough to approximate the quiet sun? Or does that small amount of magnetic field really change things significantly? And if we want to be realistic on a 10 centimeters per second scale, do we need a small scale dynamo type of model? And so in order to do that, we wanted to answer the question like, if we're comparing between hydrodynamical and small scale dynamo, is MPS Atlas going to be okay, even though it ignores the Zeeman effect? So in this particular test, what Ginger did is she looked at kind of an extreme case where the underlying magnetic field in the cube was 100 Gauss. So it's more magnetic than the small scale dynamo. And then she looked at a range of different iron lines that have different magnetic sensitivities listed here by the Landé factors. And you can see that for all the lines that have low Landé factor, we have good agreement even at 100 Gauss if we're ignoring the Zeeman effects. But for like iron, like the Hinode line, the 6302 line that's really magnetically sensitive, then you would want to make sure you're taking into account the Zeeman effect if you were starting to look at cubes that were a bit more magnetic here. But this was a proof of concept to say, look, if we're looking at just a hydrodynamical and a small scale dynamo case, we're okay to use MPS Atlas. We also then were interested in comparing MPS Atlas and Nicole to each other, as well as to some solar observations. And we saw in the past that the comparison for the against the FTS for those two other lines I showed you that had the lower Landé factor. Well, here's the really magnetically sensitive one. And you can see the different colors are the different magnetic scenarios. So you've got your hydrodynamical, so no magnetic field case in gray, your small scale dynamo one here in blue, and then your 100 Gauss one in green, and then the 200 Gauss, so you're probably closer to like a faculae or plage region here in orange, and then the observations from the Lars spectrographs are shown now in black. And actually, you can see that for the quiet sun observations on this day, we were probably somewhere in between a small scale dynamo and 100 Gauss. So we may need to, if you want to match the quiet sun, it might be somewhere in between there. So we still need to do a little bit more research into that. So now I want to talk a little bit about how we're going to take this approach and say, okay, as a whole, how do we simulate sun as a star hydrodynamical case, and how do we do it for a small scale dynamo? Well, it's not quite as straightforward as I showed, where we just map, we have an individual snapshot for every tile that there is in our model star, because there are about 20,000 tiles that would correspond to the individual snapshots then. And so that would be very computationally intensive for each one of them to have an independent snapshot. And we want each tile to have an independent granulation pattern so that we're not repeating the pattern, because that would affect how the averaging is done when you're trying to simulate a model star. So what we do instead is we parameterize the line profiles that we get out of the simulation, and then we can use those to create new line profiles that are representative of what we would have from the simulation if we ran it forward in time, quite a long time. So we do that by making cuts in magnetic field and continuum intensity. So I'm showing here an example from a 200 Gauss simulation from this proof of concept work that is highlighted below, where you've got disk center on top and then one towards the limb here. So we've inclined the boxes as well. And you can see this is just an example in continuum. And then this is what it looks like in magnetic field, where you've got the granules have advected the magnetic field into the lanes, and you can get concentrations of up to 1 kilogauss or more. And then you can see the granules themselves are pretty much non-magnetic, which breaks us down then into these 4 different components when you do these thresholding. And so this is what it looked like in our proof of concept work, where now what we did, because for each individual pixel in here, we have a line profile. We're looking at Stokes' eye in particular, so the absorption line profiles. And then what we can do is we can average together, for example, the line profiles from all the pixels of a given category, and then we can average those over a time series. And so this movie is showing you what in green, what an average granule line profile looks like as you incline the star, as well as, for example, what the magnetic bright point component or the non-magnetic lane component would look like. And then in principle, then what we can do is we've got a line profile that represents a physical component of the granulation. And then if we know what filling factors to add them up in, we can add them up and create new line profiles. So the ultimate goal is to take the filling factors from the simulation and understand their probability distribution. And then we can use that probability distribution to generate new filling factors that would be representative of what we would get if we continued to have that simulation run over a longer period of time. So this is like a cheat code in order to generate new line profiles that would represent independent granulation snapshots. So we want to do this across quite a broad wavelength coverage, but we're not sure exactly if this sort of parameterization is going to work when you move to different stellar lines. And so rather than starting at like a region of going from like 400 to 700 nanometers or something with thousands of lines, we've just started with a handful of lines here listed in this table, where you can see we've got different iron lines that have different depths and excitation potentials and Landau factors and so on. And now what Ginger is doing is specifically starting with a small scale dynamo cubes and then looking to see like, okay, does this parameterization that we saw in our proof of concept work, does it translate to other lines? And if not, why not? And if so, what is the best way to use this for when we are going to expand to thousands of lines? So of course we've changed now from a 200 Gauss to a small scale dynamo. So our threshold for continuum intensity or magnetic field might need to change, and those might need to change line by line, or maybe we will have a fixed mapping for all of our lines. It's something that's still up for debate at the moment. But what I'm showing you now is some plots that Ginger made, where on the x-axis is continuum intensity, and on the y-axis is absolute magnetic field. And then the color code is the number of pixels within the entire simulation that fall within that category. And this is for a particular iron line. And this is just an example I'm showing you for a given snapshot. So we've got like this cluster here, because it's bright and not magnetic, would be your granules. And then these ones here are a bit more magnetic and they're bright. That's your magnetic bright points. And then conversely, you get your magnetic lanes and your non-magnetic lanes here. And then this is just an example of showing that in this new cube, how those match, where the granules in this particular image are shown in red. And then what does this look like in terms of the new lines and the fact that we're using NPS Atlas, and then we have a less magnetic field? So this is just an example showing you a couple of those. What you didn't see in that original movie that I showed you is that there is some variation in what is the average granule line profile. And you can see that in these profiles, in these plots here, where these are, I think Ginger has 45 cubes with a 90-second cadence. So there's 45 individual lines that are plotted here, because this is the average granule for an individual one. And so there's a little bit of spread here. Part of that spread is because we have pressure mode oscillations that are present in these simulation blocks. And so we're still trying to figure out what is the best way to deal with those? And so one way of analyzing like how good our reconstruction is and whether or not we can remove the oscillation is to do an autocorrelation. So the concept is if this parameterization, if the time average of this is an accurate representation of what a granule is, then as long as we have added up we take the filling factors from a given snapshot and then add them up with our time averaged components, we should reconstruct the granulation component for that snapshot. And then if we compare that reconstructed profile to what we would get if we had just averaged over all of the pixels, then the only difference between those two profiles should be the oscillation, because the reconstructed profiles were created from time averaged granulation components, so they have no knowledge of the oscillation. So what we can do is an autocorrelation between the original and the reconstructed ones, and that should give us what we've deemed to be the oscillation. And so what I'm showing you here, so Ginger's made this plot, we've got time on the x-axis and velocity on the y-axis. The top plot is if we just take a template, that line profile, and cross-correlate it with our averages that we get from the original snapshots without any parameterization. So this signal should have oscillation plus granulation in it. This signal here in this panel, the one below, is the autocorrelation between the reconstruction and the original. So it should only be the oscillation. And then the difference between those two is what should be the granulation signal. And she's done this for all the different lines that we're looking at the moment. And then we can compare this, which should be like our ground state truth of the granulation, to our reconstructed RVs. And then we can look at the residual. So which is just the difference between these two, as this will tell us like, okay, are we doing a good job? If our parameterization is working well, these residuals should be really quite small. And in our proof of concept work, they were actually less than 10 centimeters per second at this center. So we're a fair bit larger here, but the amplitude of the oscillation signal is also quite a bit larger, because if you have a simulation box with a larger magnetic field, that magnetic field dampens the oscillation. And so that might be a contributing factor, but we're still looking at trying to optimize the cuts and continuum in magnetic field, which might resolve some of this discrepancy here. But that's where we're at the moment. And then we can, and this plot was all just for discenter, so we haven't moved off discenter yet. So we're still one more step to before we can start doing disk integrations. But we just wanted to show you a quick look at what those line shapes, asymmetries look like at the different lines versus the velocity. So this is the bisector span, so the average of the top of the bisector and the difference between the bottom. So it's a measure of the curvature of the line, but only looking at the reconstructed profiles where they shouldn't be contaminated by the P modes versus the velocity. And we've got a correlation as we would expect, and it seems the slope of that correlation seems to be dependent on the line depth. But that's kind of where we are in terms of moving the exploration that we had before to different magnetic field strengths and different lines. And ultimately, the goal is to look at thousands of lines. And then also to examine the impact of faculae eventually, but probably on an individual line basis, because we'll definitely need to take into account the Zeeman effect then. So I wanna switch gears a little bit now and move to a bit more empirical side of what my group is doing, because it's just like as we know, you really need to know the star to know the planet, but sometimes the planet can feed back and allow us to probe the star a bit more. And so, for example, if you take out of transit observations and subtract in transit observations, you can isolate the starlight behind that patch, behind the planet along the transit chord. And then you can measure the velocity of that. And if you understand, then you can say like, okay, what is the convective blue shift of this patch along the transit chord, and start comparing that to the MHD simulations to validate them. And in addition, because the star is rotating, you actually need to subtract the stellar rotation in order to measure that convective blue shift. And if you're measuring the stellar rotation, then you can also get a measure about how the planet is relative to its motion along the orbital plane, how that is aligned relative to the stellar spin axis, which can tell you about like how the planet might have formed or evolved over time. So this particular technique of doing the subtraction route is deemed the reloaded RM. I just wanted to highlight a few notable detections because we can push a little bit further than with the classical RM. So down to M dwarfs and really small planets here. And I want to highlight some work by a student from Geneva who looked at, okay, if you're using this technique, where's the optimal place to probe differential rotation and convective center of limb variations, as well as just highlight that Dr. Lauren Doyle and Dr. Marina Lafarga are continuing to work in this area. They've now transitioned to working in Dave Armstrong's group here, focusing on the Neptune desert, but they've got a handful of various interesting RM systems that will be coming out in the near future. So stay tuned there. Another interesting one is if the planet happens to occult a spot, then we can learn a bit about the spot itself. And so one way to visualize this is to look in photometry. Actually, it's quite conceptually straightforward here, where if the planet goes across a star spot, then what you get is this sort of bump in the light curve here. So how would this then look like in RV space? Well, now like here I'm plotting the center to limb angle of the planet. So, or of the star. So this is near decenter, this is near the limb. This is velocity on the y-axis. So this is that net convective blue shift as a function of limb angle, but showing you for two different magnetic field strengths because that alters what the convective blue shift is doing. And now if you happen to have a magnetic active region there, it's going to suppress the convection. And so if you were trying to make this measurement using the RM effect, the reloaded RM effect, what you should see in velocity space is a bump, as long as you have good enough precision to be able to do that. So the idea was to go hunting in photometry and then find evidence in the photometry that the planet has occulted a spot, and then go digging in the spectroscopy and see if we can see its signal. And so we chose WASP-85 A because these, as you can see here from these K2 observations, where these are observations of the transit where the transit model has been subtracted. So it's just the residuals, and these bumps here that you see being connected are when the planet is occulting a star spot. And so we thought, okay, this is a very active star. It happens a lot. So let's go ahead and see what we can do here. So we had quite an extensive campaign. We have simultaneous K-UPS and HARPS North data, and then we have simultaneous espresso spectroscopy with photometry from NGTS, OilerCam, and Speculus. And you can see this work is being performed by Dr. Vedad Knovac, as well as a PhD candidate from Geneva, Heretum, who's working with Monica Lindell. And so I want to highlight in particular the espresso and the OilerCam data, because these are some of our highest precision data where it's a little bit easier to see the evidence for the spot occultations. So Heretum has kindly modeled the photometry for us, and actually it looks like we do, at least in a couple of the nights, occult star spots this time. And this is one of the stars, for one of the nights, this is the star spot model that he comes up with. And this is what the corresponding OilerCam photometry, where you can see quite strong evidence for a spot occultation here, FA0 and a little bit after that. And according to his spot modeling, the spots are probably 100 to 300 Kelvin cooler than the photosphere. And on this particular night, I think they're about 12 degrees in angular size. And it's possible also, but that these might be a collection of smaller spots as well, but they can be collectively modeled by a bigger one. And then Vedad is looking at what the spectroscopy looks like. So this is just showing an example of the disintegrated RVs of espresso. And it's not immediately obvious by eye what the spot occultation is doing in terms of this spectroscopy. I don't really see bump here. And actually there are error bars on here. They're just really small. And so now I'm showing you some work he did where he's looking at the reloaded RM. So this is the local RV behind the planet. And these are the residuals that goes along with this solid body rotation model. And then in the middle panel here, I'm showing you the local full width half max of that local cross correlation function for that represents the starlight behind the planet. And then also the Euler-Cam photometry here for reference. And you can't really see it, but in the RVs, any deviation that corresponds to these spots, but you do really see it in the full width half max of that local CCF. So there is an impact that's happening, but we're still kind of probing what that is and what we can learn from it. So what Vedad did is took, like, this is an example of one of those local cross correlation functions where we're measuring the centroid of that to get these local RVs. And he went and calculated the line bisector of that. And we're looking at and saying, like, okay, how does the asymmetry change between what we think is the starspot photosphere versus the quiet photosphere? And we're interestingly, we're not, for some reason, we're not sensitive to the change in the net convective blue shift. That is not obvious because the local precision here is about 50 meters per second. And this is a G star, so we'd expect probably similar to the sun, where you'd see maybe a few 100 meter per second difference between the convective velocity in a spot versus the quiet photosphere. So we should, in theory, be able to detect it, but we're not just yet. So these ones in red are what we think correspond to the sort of spotty regions versus the more quiet ones. So there's more work to be done there. First look is we've got an obliquity near 22 degrees, but there's night to night variability. So we've got 3 nights of espresso data. And I think one other night is similar obliquity of around 23 degrees, but we have an additional night where the obliquity is around -10. Part of that might be due to the fact that the impact factor of this planet is pretty low. So there could be a degeneracy between the projected rotational velocity that we measure and the obliquity. So it's something to explore a bit more. We don't really see a big difference whether or not we use a light curve for our normalization that has the spot modeling versus one that doesn't. And that might be because of that night to night variability is dominating, or it might be because the biggest impact here happens to be at phase 0. And so that even if there was a jump or a bias, it might not affect things as much as if you had something at the limb. So still more work to be done here. And now for the last couple minutes, just switching gears one last time and talking a little bit about exoplanet atmospheres. And in particular, I want to highlight some work done by Vatsal Panwar, who's also co-supervised by Matteo Brogi as well. And looking at the case of Tau Bu, there's been a little bit of discrepancy in the literature about, like, okay, is there water or is there not water present on this planet? You can see that, like, he's done a nice summary between different observations taken in different bands and by different authors, and whether or not they found carbon monoxide or water. And the reason why this is interesting is because a detection or non-detection of water drives the inferred metallicity of the planet, and like a detection of, like, a lot of methane and a lot of carbon monoxide and a high metallicity has implications for how the planet might be formed, which I'll show you a little bit further later on. So for this, we're still doing cross-correlation, which is what we've kind of been a theme throughout this high-resolution spectroscopy talk. But in this case, we're doing cross-correlation with the planetary atmosphere. And in this case, Taboo is a non-transiting planet. So we're looking, and so the velocity changes over the course of its whole orbit by like 100 kilometers per second or so. So it's quite a large change in amplitude when you're thinking of it there. But the planetary atmosphere signal is quite small compared to what you would observe, which is a combination of the stellar atmosphere and the planetary atmosphere, illustrated here by blue, which is the sort of noisy stuff that you would actually observe. But if you use your high resolution model for your planetary atmosphere, and you take advantage of the fact that you've got thousands of lines that when you do this cross correlation, you can build up and start looking and dig out these faint signals. These are, in the bottom right is some of the results of the sort of traditional way of showing you of your KP, which is the amplitude of your planet. Hold on, I wanted the movie to go away. So you can actually see the plots versus the VSIS, which is your systemic velocity. And basically, if you see a nice little bright blurb here, it shows that we've probably got a detection. And so we don't really detect methane, we do detect carbon monoxide and a tentative detection for water. Showing you just here in the corner plots, you can see it a little bit better. And just highlighting here that this particular axis here is a scaling factor that is needed because it's a non-transiting planet and we have uncertainty on the radius. This corresponds to a particular temperature pressure profile for the planet. And in this case, we've got a non-inverted profile, so we should be seeing absorption, which is what we see. So I mentioned that the ratio between like C to O and metallicity, that has implications for how the planet might be formed. This is just showing you some result from some simulations compared to where we think Taboo sits. Where if you were sort of in this regime in the upper left, you're probably gas-dominated accretion, and in the bottom right, you're probably planetesimal-dominated accretion. Taboo, our result sits, well, Vatsal's result sits about here, but there's quite a large uncertainty on it. And so we can't really rule out the fact that the planet might be in this regime here, which can't be explained by the core accretion model, which makes it kind of interesting for further study. What might be of interest to this particular audience is the fact that the telluric contamination was critical to get the correct abundance. This is just showing you an example of like if you didn't correct the residuals, you end up with this signal here, and then when you do correct them, you get rid of that sort of artificial signal. He does a PCA principal component analysis on the tellurics, and looking at like this is just showing you if you had 6 principal components versus 7, what the removal is. But even after you remove them, so in this case, all the tellurics are these vertical lines that you see in this plot, and then he's done his PCA and removed them, and then this is what you get left over. But you can see there's still signatures here, and if you don't remove those, then you can get the wrong abundance for your characterization. So what he's done instead is just gone ahead and masked those out. But the connection of his future work is going to be more closely tied to what this audience is interested in. So he's shown now that like, okay, you really need to get your telluric correction done properly in order to get your planetary abundances correct. But what about if there is stellar variability on the surface? How does that affect your planet abundances, or what you would measure? And so this has been explored a bit in the low resolution transmission spectroscopy side of things, but it hasn't really been explored at high resolution, and that's where Vatsal is going to go. So he's got this similar to Ginger. He's got this idea of this model star that's gridded up, and you have you can inject whatever spectra you want into these tiles. And in this particular case, like what he's going to be doing is injecting spectra that would represent a spot photosphere in these tiles, whereas all the other tiles would get like a quiet, quiescent photosphere. And then we will treat the planet as an opaque occulting sphere that goes through. And if it might be the case that like if you just had the planet on its own, you would get some sort of detection map that looks like this, where you've got your nice KP versus VSIS right where you expect it. But if you had an unocculted star spot, for example, contaminating your measurements, you could possibly end up having that skewed. So his work is going to be exploring that. And at the moment, what we are going to do is just use 1D model atmospheres from Phoenix and inject things of different temperature, essentially, and possibly accounting also for the convective blue shift changes. But that's the next step once this paper is published, which should be submitted in the next week or so. So I will just kind of wrap things up. This is the group as it stands. Also highlight that Annalise, Mathieu, and I are interested in trying to create a network of stabilized high precision spectrographs. If you're interested in that and you haven't already spoken to us, please do speak to us. But yeah, ultimately, if the big take-home message is that the interplay between convection and magnetic fields drives most, if not all, stellar surface variability. So us exoplanet researchers desperately need solar and stellar physics to disentangle the planetary signatures, whether that be from a planet hunting point of view or planet characterization point of view. And then there's a nice cheeky bonus that transiting planets can be used to spatially resolve the stars and feed back information. So I will leave it there and take any questions if we have time.
We do. Thank you so much, Heather, for an excellent talk. Yeah, please use the clapping emojis to show appreciation for that wonderful presentation. If you have questions for Heather, please feel free to raise your hand using the raise hand button or to pop them into the chat, and I will call on folks. While people ponder, I will kick things off. So going back to, I believe, Ginger's work earlier in your talk, you mentioned that you're starting with this subset of lines, iron lines, and also starting in the disk center. It sounds like possible areas for expansion are both moving to the limb of the star so you can do full disk integration, and then potentially down the line adding more lines to your analysis. Is there a tipping point that you anticipate where X number of additional lines might reveal more nuanced details of this process? Or do you think that, working with this subset is a sufficient approach for now?
Yeah, so I think that ultimately you want to move to as many lines as you can. And for a case when we're looking at like hydrodynamical or small scale dynamo, I think that we may as well use all the lines. Computationally, we can do it. The reason why we haven't started with that is because we're not sure if the way that we're parameterizing this granulation, if it translates across all those lines. And if we can show it on a handful of lines that it does, then hopefully that is the case for thousands of them. But I do think that we might, like when we are getting to regions when we have increased magnetic field, we need to account for the Zeeman effect. So that either means we're going to have to do individual lines, in which case then we will just be stuck and there's nothing else we can do other than pick lines that are characteristics across the spectrum and be like, look, if we can characterize these 10 lines that have these characteristics, we can translate them and interpolate across to other lines. For example, like if we go back to one of the like bisector plots, like here, for example, like you can, like weak lines can be thought of as just contributing to like this part of the bisector, and then deep lines are contribute to all of it. So like there is already knowledge to say that we might be able to interpolate in between, like if we have enough lines, like what is happening for the other ones. But of course, if you can do all the lines, it's better. But when we are also exploring just like accounting for the Zeeman effect in MPS Atlas, and we're not sure how much that's going to slow things down. So far, I don't know of anyone that has done like a full EPRV high resolution spectrograph of where you also take into account the Zeeman splitting when you're doing your line synthesis. But I would be interested to know if there is, and I'm just missing it.
Gotcha. Okay, thank you for that. John, I see your hand up. Go right ahead.
Yeah, thanks. Really interesting talk, Heather. Thanks for that. A question about the star spot crossing events that you were looking at photometrically and with RVs. Are there any limitations to extending to other systems? Can you extend this to M dwarfs without a problem?
Yeah, we should be able to. I mean, I guess the tricky thing is probably a signal to noise thing. So you want to make sure you have the signal to noise to be able to resolve them both photometrically and spectroscopically. So like one interesting thing is Vedetta has noticed that actually although we're not seeing it in the RV, we're really sensitive in full with half max and possibly more sensitive in full with half max of our local one than we are in photometry. So it might be like, I would say that like, I think you still need to have high resolution in your spectrograph in order to be able to resolve the shape changes. And then it's a signal to noise thing. I mean, also like if the star is rotating very slowly in terms of like trying to get the obliquity and stuff, then that can be difficult. So sometimes M dwarfs are hard for that reason, or they're hard because they're faint. But we've shown that like doing this technique, at least with the reloaded RM, we can be more sensitive for M dwarfs possibly. And we don't have to make assumptions about the shape of this local profile. Whereas when you do like classical RM modeling, you do analytically make an assumption there. Whereas if your M dwarfs have sort of a funky shape, we would be able to account for that a little bit more. But it could be interesting. I think Lauren Doyle does have some observations on Spiru, I think, where she's trying to do this, where we're of an M dwarf. So we're looking at I think it's an active M dwarf and hoping that it'll call spots. And we chose a spectrograph that is a bit more tuned in for those M dwarfs. So
Yeah, and I was even gonna amplify on that. There are a handful of systems with persistent spots.
Yeah.
Be prime picking, because then you know that there's always going to be a spot there in your observation. So
yeah, because that one of the tricky things about WASP-85 A is it's a close binary, and so trying to figure out the rotation period is difficult because it's a little bit contaminated by that other binary. And then like if you really nailed down the rotation period, and then it would help you figure out like, are you seeing the same spot again? You know, and it could help you probe the spot lifetime and stuff. But this was a good system because it occults them multiple times, but difficult because it's a close binary as well.
Okay. Any last questions for Heather? Just over the top of the hour, so it might be time to wrap things up. Okay, if not, let's thank Heather again for an excellent presentation. As always, the recording will be posted to the Google Drive after the fact. And as a reminder, no colloquium next month in March because of extreme solar systems. We'll be back in April, and so I'll send announcements about that in the coming weeks. Thank you so much, Heather, for taking the time to talk to us, and hope everyone has a great rest of their Thursday.
Thanks, everyone.